All right, welcome everybody. So in this video, I want to introduce the idea of what a quadratic form is in Rn, and then take a look at some examples. So a quadratic form on Rn is a function that takes an element from Rn. So the input into this function is a vector from Rn. And so we input a vector x into this function, and this function q, any function q, which can be defined in the form where this is the output is going to be defined as taking the transpose of x, so this would be like a row vector, times an n by n matrix A times the column vector x, where A is a symmetric matrix called the matrix of the quadratic form. So any function q which has this form is what's called the quadratic form. And what's important here, again, is that this matrix A is a symmetric matrix. And we call this the matrix of the quadratic form. So let's take a look at a couple of examples. Okay, so the first example I want to consider is, let's consider R4. So let's let x be a column vector in R4. And let's consider the usual standard inner product on R4 that we've defined, which is the dot product of these two vectors, which we can write as the product of x transpose and x, which would give us x1 squared plus x2 squared plus x3 squared plus x4 squared, which is how we define the magnitude of x squared. So this is a very familiar function that we've seen in the context of inner products in calculating distances and angles. And notice that this function, when we write it in terms of the entries of the vector x, is a quadratic function. So it's not that surprising why we call this a quadratic form. And in this case, this is a quadratic form because I can write this function as x transpose times the identity matrix. So in this case, this would be the 4 by 4 identity matrix times x. So in this case, the matrix of the quadratic form is the identity matrix. We get a very standard matrix for the quadratic form, the identity matrix, because we've chosen maybe what is the most natural sort of quadratic form on R4. Okay, let's consider another example. This time we're going to consider a quadratic form that we define on R2. So here our vectors are column vectors with two entries, x1, x2. And in the first case, we defined the inner product. Well, first we listed out the function, the quadratic function of the entries x1, x2, x3. And from this, we were able to identify the matrix of the quadratic form. In this case, we're going to start with a given matrix of the quadratic form. And let's write out what the corresponding formula is for this quadratic form in terms of the entries of our column vector x1 and x2. And so notice this is a quadratic form because this matrix A is a symmetric matrix. The entries off of the main diagonal have this mirror image property. So if we go ahead and take the product of the transpose of x, the row x1, x2, times this 2 by 2 matrix, then what we get is a 1 by 2 matrix. So we get a column vector back. The first entry is x1 minus 4x2 by taking x1 times 1, x2 times minus 4. The second entry in this row is minus 4x1 minus 5x2. And then we multiply this by the column vector x1, x2. And that gives us x1 minus 4x2 would get multiplied by x1, and then minus 4x1 minus 5x2 gets multiplied by x2. And so distributing terms and grouping things together, we get the following formula that q of x can be written as x1 squared minus 8x1 x2 minus 5x2 squared. And so notice here the coefficient that is in front of the x1 squared term, that's the coefficient that's the first entry on the diagonal, main diagonal. The coefficient in front of the x2 squared term, the minus 5, that's the second entry on the main diagonal. And then for this entry, the minus 8, we split that in half, and this gives us the symmetric off-diagonal entries of minus 4 and minus 4. So on the next slide, in the next video, we'll go through a number of examples where we're given a formula and we want to figure out what the matrix for that quadratic form is.